very happy to have our old friend, John Ellis, coming back to visit us. We were just trying to figure out how many times. Well, apparently the first time was in 2000. He coming here, attended some conference. Now he's coming back again. This time, this morning he had just given a summary talk at the Pascal's, particle strengths and the fields. So now this afternoon is giving us the Colloquia. Well, John is now the Maxwell professorship at King's College. He obviously look at it there. He also continue to work at CERN. John graduated in 1971 from Cambridge University, and then after postdoc at Caltech, ASIAA, went to CERN. He has been there from 73 to 2 years ago. Now, still has same as the affiliation. He was the theory division leader for many years. I worked in CERN for 1 year as a postdoc in 1990 to 91. At that time, John was the head. So so glad to see John again. And here, John has done many interesting work. Well, if anyone of us do one piece of the work, we would be very happy. But he has really done a lot of very important work for establishing from a standard model confirmation. Many of the things. One of the things is the QCD when was established, the gluon stuff have never been seen. He was one of the first. He's the first theorist to really find a way to guide the experiment, how to find this gluon jets from the experiment. So that was 1977. Then after 1 year or two, the experiment found it. Well, see, this year the Nobel Prize was awarded to Ellis and Higgs. Well, John has been working on this for a long time. In 1974-75, he has already studied many of the great details of Higgs physics. If you look at some of the branching ratios shown today, look very similar, but of course some parameters are changed. Well, this morning he will say, well, in that paper, he said, well, should not, at that time, experiment should not look for that Higgs, but now it's been, so experiment didn't look for his advice, so they found the Higgs. But so today, we have already found the Higgs, so after the Higgs, what are we going to do? So then you see the title beyond the Higgs Boson. So let's welcome Professor John Ellis for our talk.
So thank you very much for that kind introduction. It's a pleasure to be back in Taiwan. So this picture here shows you the outline of the Large Hadron Collider, the LHC at CERN. And that's Geneva Airport. So that tells you how big the Large Hadron Collider is. The circumference is 27 kilometers. Of course, from the surface, you don't see very much because it's on average 100 meters underground. And around the edge, there are 4 places where there are big experiments. So those experiments last year discovered a particle that we now consider to be a Higgs boson. That, of course, is not the only thing that I should figure out how to. That Higgs boson is not the only thing that we're looking for at the Large Hadron Collider. And in this talk, I will try to give you a little bit of background about the Higgs boson, the standard model, what may lie behind it, beyond it, and what we're still looking for at the LHC. So I like this picture, which shows Peter Higgs in 1965, when he was actually visiting in the United States, and he was working out in some detail the theory, the phenomenology of the Higgs boson. It was actually quite a remarkable paper that he wrote at that time, discussing how the Higgs boson might decay into pairs of massive vector bosons and all sorts of things. So if you could look in detail at his notes, probably you could steal a few good ideas. So the Higgs boson can be regarded as somehow the crowning piece of what we call the standard model of particle physics. So as you probably know, this was proposed by Abdus Salam, originally from Pakistan, and two American theorists, Glashow and Weinberg, in the late 1960s. And they made essential use of the ideas of Peter Higgs, Grout and Englert that we'll come back to later on. The first experimental tests of the theory came in the 1970s. In particular, it was a crucial experiment at CERN which discovered a new form of weak interaction in 1973. You don't see so many people wearing white coats these days. And if you visit CERN, you can actually see the piece of experimental apparatus where this experiment was done. So in the 1980s, 1990s, many other experiments confirmed predictions of the standard model. In particular, there was a series of very accurate experiments done at CERN in the 1990s with an accelerator called LEP, which verified the predictions with great accuracy. There you can see a little dot that's actually exaggerated in size. The experimental measurement is smaller than that dot. It agrees very well with the theoretical calculation. So this standard model, obviously it contains nanoparticles. So there's the electron, two heavier charged leptons that Leon discovered in cosmic rays, the tau discovered in accelerators. Correspondingly, there are 6 quarks over here. The up and down that make up regular nuclei and others that were discovered in cosmic rays and in particle colliders. And then in between here we have 3 neutrinos. The fact that there are just precisely 3 neutrinos was established by the experiments that I showed on the previous slide. And of course now there's a lot of physics interest in studying the properties of those neutrinos, but I won't go into that in great detail in this talk. So we distinguish 4 different fundamental forces between these nanoparticles. So 2 of them, of course, very familiar from everyday life, gravity, electromagnetism. I'd like to remind people that electricity and magnetism were actually the first interactions to be unified, almost exactly 150 years ago, by James Clerk Maxwell when he was professor at King's College London. Anyway, subsequent to that, 2 more interactions were discovered, the weak and strong nuclear force. Xiaogang mentioned QCD, that's the theory of the strong nuclear force. The weak nuclear force, this was studied with high precision in the experiments that I just mentioned, and all the predictions agree with the standard model. So I like to think of the standard model as in some sense representing the cosmic DNA. Those particles, those interactions encode all the information you need to make all the visible stuff in the universe, including ex-President George Bush. Except, there's just one thing missing. And that is, where do the particle masses come from? And this was a puzzle for many years. Particles have to have masses. If the electron didn't have a mass, there wouldn't be atoms, because the electron would run away at the speed of light. If the quarks didn't have masses, nuclear physics would be completely different. If the W didn't have a mass, the weak interactions would not be weak. So we need to understand where particle masses come from, and that is where Mr. Higgs and his friends came up with the theory. Okay, so a little bit more mathematical detail. Here is the structure of the standard model. So here we've got the 3 neutrinos. They are accompanied by 3 charged leptons. We've got 6 quarks. These particles have somewhat strange quantum numbers, and one of the issues in physics beyond the standard model is to try to explain why those particular particles, where those quantum numbers come from, and so on. So this is the Lagrangian of the Standard Model, which you can also see on my t-shirt. So I hope this laser is not very powerful. So the top line, this describes the fundamental forces. The top line actually is sort of basically a generalization of Maxwell's theory that he wrote down in 1864. The second line, that describes how those forces act on the fundamental particles. The third line, that's how, according to Higgs et al., particles get their mass. And the bottom line, that actually represents the structure of the Higgs theory. So, until last year, there was no direct experimental evidence for the two bottom lines. The two top lines, those were verified, those were checked in many detailed experiments. But the two bottom lines, those were hypotheses until July the 4th last year. So as I said, the Standard Model agrees perfectly with all the confirmed accelerator data. And that agreement works if and only if there is a Higgs boson or something very similar that does the same job as the Higgs boson. And in fact, for something like 20 years before the discovery, we were working to try to predict what the mass of the Higgs boson should be. And this agreement of the Standard Model worked okay only if the Higgs boson was relatively light within the range of the Large Hadron Collider. Of course, there's plenty of other problems, and I'll mention some of those later on. So this is a summary of the information that we had about the Higgs boson in 2011, just before it was discovered. So experiments at previous accelerators had not found the Higgs boson. So there was a range of mass up to about 140 GeV. We knew it wasn't there. Experiments at Fermilab in the United States had shown that it was not around 160, 170 GeV. And the agreement of all those precision measurements with the predictions of the Standard Model indicated that it was probably somewhere near the bottom of this curve here, around 125 GeV. And in fact, a group of experimentalists who did this analysis of the data predicted back in the middle of 2011 that the mass of the Higgs boson would be 125 GeV plus or minus about 10, corresponding to that uncertainty down there. And so you might say that all that's happened in the 2 years since then has been their prediction has been confirmed, and the error has gone down by a factor of 10. Clear pointer? This works so well. Okay. I'll stick with what I got. Okay. So, of course, this existence or not of the Higgs boson is only part of the story that I want to tell this afternoon. And I'm going to be looking in particular later on at other issues beyond the Standard Model. Like, for example, why are there so many different types of matter particles? Why are there 3 neutrinos? Why not 2? Why not 1? There's a theory that that might possibly be connected with the existence of matter in the universe. Matter. Well, how about the dark matter? I said that the Standard Model explains all the visible stuff, but astronomers and astrophysicists tell us that there's maybe 5 times as much invisible stuff that may be made of particles that perhaps we can make at the LHC. I talked about all those different fundamental forces, strong, weak, electromagnetic, gravity. One would like to unify all those into a single, simple mathematical description. And by the way, while we're talking of gravity, it's perhaps one of the greatest shames of theoretical physicists that 100 years after quantum mechanics was discovered and general relativity, we still don't have a true quantum theory of gravity, at least not one that's actually been proven to be correct. So in some way or another, the LHC addresses all of these issues in physics within and beyond the standard model. And okay, clearly we think we made a lot of progress on this first issue, but I will be discussing in particular later on how one could make progress with some of these other ones. I should say that doing collider physics experiments, in particular at the LHC, is of course not the only way we study these fundamental issues in particle physics. So the LHC, it's got a lot on its plate, dark matter, Higgs Boson, and so on. But many of these ideas may appear only at energy scales which are far beyond what we can achieve, at least with the LHC. And that's where astrophysics and cosmology come in as potentially giving us additional information. And I think one of the interesting aspects of the PASCOS meeting over the past week has been precisely how there are these complementary approaches to looking at fundamental physics. That said, in the rest of this talk, I'm going to be focusing maybe on this. Okay, so the origin of mass. So of course, Newton told us that weight was proportional to mass. Einstein told us that E is equal to mc squared. Unfortunately, these guys somehow forgot to explain where the mass comes from. And that's where Peter Higgs comes in with his theory. And it's a key aspect of his theory that there should exist this particle that we call the Higgs boson. So if you look on the blackboard, you can see phi, that's a field. Electromagnetic field has a quantum associated, called a photon, the same way that Higgs field has a quantum associated with it, that's the Higgs boson, which became, between 1964, when the theory was postulated, and last year, in some sense, the holy grail of particle physicists. And you can ask yourself, what do you do after you've discovered the holy grail? So, I'd like to present you with a little analog, analogy for thinking about the way in which this Higgs mechanism works. So I talked a moment ago about this Higgs field phi. See it there. Okay. So, like electromagnetic or gravitational field, this is a field that is present throughout all space. There's an important difference between the Higgs field and the electromagnetic or gravitational field. Those fields have sources, electric charges, the sun. The Higgs field, on the other hand, is thought to be universal, medium, present everywhere in the universe, completely homogeneous, completely isotropic. So my proposed analogy is to think that you're in the middle of Siberia, it's winter, there is snow everywhere, apparently infinite, in all directions, featureless, flat, universal medium. Now if you're a particle propagating through that Higgs field, you may be like a skier who is trying to cross that snow. If you're a skier, you don't sink into the snow. In some sense, you don't interact with that snow. You skim across the top very fast. That's like a particle with no mass that does not interact with the Higgs field. Photon, maybe. On the other hand, maybe it has snowshoes. If it has snowshoes, then you sink into the snow, you interact with that Higgs snow field. You travel slower than the skier, like a particle traveling at less than the speed of light, an electron maybe. And then finally, if you're really unlucky, you don't have any ski equipment at all, you're trying to walk across Siberia, you're going to interact very strongly with that Higgs snow field. You're going to go much slower than the skier, much less than the speed of light. That's like a particle with a very large mass. So then the next question is, what is that universal Higgs Snowfield made of? Well, we all know what snow is made of. The quantum of snow is a snowflake. So the Higgs boson, that's the quantum of the Higgs field. Now, you can carry this analogy a little bit further. Of course, there's an infinite number of different types of snowflakes. All snowflakes are different. And that is possible because those snowflakes are in fact composite objects. They're not elementary objects. They're made up out of water molecules. So in the same way, there's a big debate taking place at the moment amongst particle physicists. Is the Higgs boson an elementary particle, or is it in fact a composite object made up out of something smaller? I'll come back to that later on. So, as I also commented this morning to the Pascos meeting, when the Higgs boson was discovered last year, the Economist, which is a sort of right-wing British news magazine, had a cover article about the discovery of the Higgs boson. And they had this rather nice graphic about the time difference between when a particle was postulated and when it was discovered. And in the particular case, of course, of the Higgs, there was a long time between when it was proposed and when it was discovered. Actually, I cheated a little bit. It was actually a little bit older than this when he actually proposed the Higgs boson. This is his passport photograph. So, I've talked a lot about the Higgs boson. Now let me be historically a little bit more accurate. So this idea of giving masses to elementary particles via a field present throughout all space was actually first proposed earlier in 1964 by François Englert and Robert Grout. And there were precedents for their theory in condensed matter physics. So here, at the top here, I have Nambu, Goldstone, Anderson, before Englert Grout, then Higgs. Higgs wrote two papers in 1964. The first one was clearing up some technical problems in how you would actually make this mechanism work, and then the second paper was actually proposing a concrete model. And then, following him, another group of authors, later on that same year, that was Graunik, Hagen, and Kibble, also proposed the mechanism. About M and P. So there is a truly remarkable paper written by two Russian theorists, Migdal and Polyakov, which was sent to the journal in 1965, although it's believed that they actually did the work perhaps already in 1964. How many people here are under 19? Nobody. Too late. These guys were 19 when their paper was written. So with all these people who were working on this theory, why is it that we talk about the Higgs boson? That's quite simple. It's because out of all these people, Peter Higgs was the only one who commented on the existence of this massive scalar particle that would be the key experimental signature for the idea. So this describes a little bit the way this thing works. So the idea is spontaneous breaking of symmetry. You have this field, and this field discriminates between different directions in the internal space of the theory. And the simplest model for this, actually proposed really by Goldstone, is this sort of Mexican hat potential. So the symmetric field configuration is unstable. The system tries to find the lowest energy state, but you've got a degenerate ring of equivalent states. And when you choose one of those positions, one of those directions, then you are breaking spontaneously the symmetry. Now, associated with such a theory, there is necessarily a massless degree of freedom corresponding to going around the bottom of the potential. And it was Nambu, who introduced this idea into particle physics, and the pion in QCD can be interpreted as approximately a Nambu-Goldstone boson. Now what Onler, Granick, Hegel, Gibble, and of course Higgs did was to show that you could give masses to vector particles by combining them with this Nambu-Goldstone boson, and that way you got a massive particle. But the additional contribution that Higgs made, and that's why it's called the Higgs boson, as I said, is to point out that this theory necessarily has a massive scalar particle corresponding to running up and down the side of the potential. And it was the discovery of that particle last year that finally convinced everybody that this sort of theory was correct. And if you look at the citation for the Nobel Prize, it does not say for the discovery of the Higgs boson. It says for a mechanism for giving particles, evidence was provided by the discovery of this particle. So as Xiaogang mentioned, I got interested in this back in 1975 at a time when people didn't know the theories of the fundamental interactions. Spontaneous symmetry breaking was a speculation. Nobody knew what the mass of the Higgs boson might be if it existed. And that was why we wrote in our paper that we don't want to encourage big experimental searches. On the other hand, we said the people doing experiments where it might show up should know how to look for it. Well, unfortunately, experimental colleagues did not take our advice, and they went ahead and invested billions of currency units in looking for this particle. So this is an example of what those experiments were looking for. So this is a computer simulation where two protons collided along this axis here. In that simulation, they produced dozens of charged particles, some neutral particles. You can see the charged particles coming out. You can't see the Higgs. The Higgs is a neutral particle, very unstable. All that you can hope to see is what it decays into. And in this simulation, it was these two energetic particles over here and those two energetic particles over there. So that's an example of what the experiment set out to look for, and later on I'll give you an update of what they actually found. However, this is, as I've been trying to emphasize, not the only thing that the LHC experiments are looking for. I talked about dark matter. So astronomers tell us that they need dark matter in order to hold galaxies together, otherwise they would spin apart. Centrifugal force. You need some centripetal force to hold them together, and that's provided by the gravitation associated with dark matter. Dark matter may be made of particles that perhaps we can make in the LHC, like, for example, supersymmetric particles, and I'll come back to those later on. So how are the experiments trying to find supersymmetric particles, or dark matter particles in general? So you can't see a dark matter particle. By definition, it's dark. It doesn't have electric, magnetic, or strong interactions. But it does carry away energy and momentum. So you look for events where there's energy and momentum carried away that you can't see. And you tell that there was missing energy and momentum because the momentum is not balanced in the event. So it's a bit like you're playing billiards, and you have balls colliding, and all the balls go off to one side, nothing to balance momentum on the other side. That doesn't happen. Same way in particles, it doesn't happen. So if you see an event like this one up here, which is sort of lopsided, whoops. Lopsided like this one, where there's energy coming out down here, but not on the opposite side, then you say, well, maybe you produce dark matter particles. So another thing which we're looking at is antimatter. Not because we want to power up the Starship Enterprise, and not because we want to fill up matter. I can assure you, we can't make enough antimatter to fill up matter. We're interested in the question of why matter and antimatter